Okay, so I think we are on, yeah, it's 6, so we can start. So in the last lecture, we kind of spent 1.5 hours defining what is a generative model. And the definition that we kind of arrived at is that a generative model is a class of model that allows us to learn the distribution of the data either uh, explicitly or implicitly. I mean, you might not know the exact expression, but it allows you to learn the distribution of the data, which in turn can be used for generating new samples from the learned distribution. Right? So that is the definition. We said that the world view I want you to have is that any data you have, any experimental data you have is coming from some distribution. And because it is coming from some distribution, the idea is if you can learn that distribution, then you can sample from that distribution. And if you sample from that distribution, each sample is like performing an experiment. And those data you are generating is like your synthetic data, right? And that is where we stopped in the journey of defining this generative model. We discussed about measure, we discussed about probability measure, we discussed about what is a random variable, uh, we discussed about the probability space. We discussed all of this, but the ultimate take home message from the last lecture was what is a generative model. And it's a model that learns the distribution and allows you to sample from it. So that means it allows you to generate new data from the distribution from which your original data was obtained, right? So that is what we uh, discussed primarily in the last lecture. So let me write this down, this definition, and then we'll proceed with the lecture today. And for today, our goal is actually to review. So we'll be reviewing different aspects of probability theory. The many of those things will be a repeat for you. Most of you are probably aware of those, be it the sum law, the product law, Bayes law, independence, conditional independence, uh, what is a PDF, what is a PMF, uh, and then maybe some of the advanced topics like, again, scale divergence, why is it called a divergence, maybe Jensen's inequality a little bit, and transformation of distribution definitely. So that is more or less the plan for today, to review probability and statistics. Okay. And the next lecture we'll try to review very quickly some basic neural network stuff, and then we'll proceed with the main content of the course, which is generative model, right? So that is basically the idea. Okay. So with that background, let me first is happening. Okay. Why is it not working? Oh, it's working. Something is happening here. Oh, it has become insensitive. Anyways, so generative model. Model. And the definition we said is it's a class of model. Now, when I write it's a class of model, you should read it's a class of machine learning model, right? When I write it's a class of model, it's a class of machine learning model. So it's a class of machine learning model that allows us to learn the distribution, of the data. And when I say learn the distribution of the data, again I'll remind you, it need not learn it explicitly, it can be an implicit representation as well. So when I'm saying learn the distribution, it is learning either implicitly or explicitly. Again, something to be noted, right? So learn the data, so implicitly or explicitly. So it's a class of model that allows you to learn the data and sample from it. It not only allows you to learn the distribution, but you can now use that to sample, which means to generate new data. Data that you have not observed, but data that is from the same distribution. Assuming you have learned your model or trained your model adequately and the learning is perfect, so all of those will come later. But yeah, and sample from it. So this is the definition of generative model that we arrived at in our last lecture, right? And when I say distribution, it means PDF. PDF, as I said, is the induced measure from the probability measure, because from the definition of random variable, you reach this thing, right? And we discussed all about this, right? So now I will take a break from this generative model business, and we will discuss about usual probability stuff, probability and statistics, the usual things. We'll discuss about that for the rest of the lecture today. We will not come back to generative model today. We'll probably not even come back to generative model in the next lecture. But after that, we'll only be talking about generative models. So for the remaining of today's lecture and probably the next lecture, will not come to this definition. But this definition is very important. This is what the course is about. And we will be spending almost all of the lectures in this course on this definition only. So it is very important that you learn and know and have an understanding of this definition. Okay. Okay. So now with that background, let us now go to probability and statistics. Okay. And in probability and statistics, we already defined random variable, which actually comes much later in the probability and statistics course. If you take a prob and stat course, random variables actually comes much later, but we defined it last time because we needed it. We required it for defining this generative model, right? But let us go back, and if I go back, the probability and statistics, it starts with the probability axioms. So there are three axioms. Kolmogorov axiom is what you call it, and those are very similar to how I defined measure last time. The same properties more or less holds. The probability of a null set is 0, probability lies between 0 to 1, and probability of union of disjoint events is equal to sum of those events, right? So I will not go there, but let me start with the two laws of, or two rules, I will say, of probability that are the fundamental building block of a probabilistic machine learning course, be it deep generative model or be it the usual introduction to ProbML kind of course where you learn about, let's say, Markov chain Monte Carlo, conjugate prior, and all of those things, right? And these two laws, anyone is aware of what are these two laws? One is the sum law of probability, the other one is the product law of probability, right? So there are two laws primarily that we need. My pen is creating a lot of problem today. Sum law of probability Anyone can define it for me? What is the sum law of probability mathematically? Any idea what is the sum law? If you have joint distribution of multiple events, or let's say 2 events for now, and if you sum over one of the events, you get the distribution of the remaining event, which means if you have probability of, let's say, A comma B, and let's say you are summing over all the possible values that B can take, then you will get probability of A, right? If you have a joint distribution, in this case it's a joint event, so probability, but it can be a PDF also. If you have a joint PDF, let's say, of 2 events X and Y, and because it's PDF, summation will become integration. So if you integrate out one of the variables, then you get the distribution of the other variable. And when you do this operation, this is known as marginalizing out. So whatever you are summing over, you are marginalizing out that variable. And whatever is the remaining variable, that is the distribution you get, is known as the marginal probability in this case. And if it is a distribution, then you will call it the marginal distribution. Okay. So this is the sum law, and this can be A comma B comma C also. It need not be 2. It can be A comma B comma C comma D, and you can do the summation over each one variable at a time, over multiple variable at a time. Whatever variable you sum over, that variable will not appear because you have integrated it out. The remaining variables will appear when you. So for example, if I do it in general sense, let's say, so in a general sense, if I do it, so probability of, let's say, I have A1, A2, AN, and let's say I'm summing over A1. What will I get? A2 to AN. A1 I am summing over, that will not remain. Okay. If I do another summation, then let's say I am summing over AN, then I will have A2 to AN minus 1. So whatever I am summing over, that does not appear on the right hand side, and remaining things appear. This is the, this will be A2 AN minus 1. Okay. And this comes directly from the joint distribution table. If you take the joint distribution table, you can easily prove this thing. Let me take one. For example, let's take the simplest example possible. I have event A1, let's say, is for me tossing a coin. Event A2 is throwing a dice. Okay. So you have, let's say, this is my A2, this is my A1. A1 is my tossing a coin. What are the possible outcomes of A1? Head and tail. So let's write it, head and tail. A2 is how many outcomes? 6. Let us write that. 1, 2, 3, 4, 5, 6. Right? So now you can create the joint probability table. I will not calculate all of those, but okay. Okay. So now let's take a random box here. Let's take this box. What does this box indicate? Getting a 4 and a tail. What is the probability of that? If I assume the coin is unbiased, the dice is unbiased, everything is unbiased, then 1 by 12. 1 by 6 times 1 by 2, right? 1 by 12. And you can understand each of these box under this unbiased assumption will be 1 by 12. Everyone follows? This is school level maths actually, but and I am not writing, right? Now, what does the sum law say? If I integrate over one of the event, I should get probability of getting the other event, right? So now, suppose probability, I want to find out, let's say, A2 is equal to 1 is what I want to find out. Probability that A2 is equal to 1. That is, what is the probability that if I throw the dice, I will get 1. From the sum law, this is equal to probability of A2 equal to 1, comma, A1 is equal to head, plus probability A2 equal to 1, comma, A1 is equal to tail, right? That is what the sum law is saying. Now, each of these right hand side quantity is equal to 1 by 12. 1 by 12 plus 1 by 12 is equal to 1 by 6. What is the probability of getting 1? 1 by 6. Similarly, if you do a summation along the column, you will get 1 by 12 plus 1 by 12 plus 1 by 12 6 times. So, you will end up getting half. Probability of head is equal to half. So, this is exactly the sum law of probability, which comes from just the joint distribution, joint probability table. But what we will be needing for this course is probably not this kind of discrete things. What we will need is the integral form primarily, and instead of probability, it will be the PDFs, and it will be basically when you integrate out one of the variables in a joint PDF, you should get whatever the marginal PDF. Okay. So, if you have a joint PDF of x and y, you integrate over y, you get PDF of x. So, for example, if I write that down, if I generalize it, what I just now said, integration of f xy, where f xy is my PDF, joint PDF of x comma y. Again, this notation I will come to later, but let's see. Let's say dy, I will get f x x, and the integration obviously is from minus infinite to. Okay. Clear? What is the sum law? The other law is the product law. Okay. So, let us go to the product law next. Product law. Product law is basically when you have a joint distribution, how you can decompose it as product of two probabilities, right? That is what product law is. And this is the law all of you are aware of, maybe by not by this name, but probability of A comma B. And when I write A comma B, that means A intersection B, by the way. I mean, keep that in mind. I mean, intersection and comma, they are the same thing. Okay. So, A comma B means A intersection B. It is the joint probability. This is equal to probability of A multiplied by probability of B given A, where B given A is your conditional distribution. It is the probability of B given A has occurred. Okay. Whereas the probability of B, only probability of B is what I did above. So, that is the marginal distribution. So, what are the distributions you have, or what are the probabilities you have? You have the marginal probability, you have the joint probability, and you have the conditional probability. So, these are the three terminologies that we will be playing with in this course. You should be knowing what is marginal distribution or marginal probability, what is joint probability and joint distribution. And lastly, what is the conditional probability and conditional distribution. Okay. And one more I will tell. So when you condition on something, that means that thing has already occurred, which means for that instance that is deterministic. So for example, A, or let's take that A1 comma A2, right? A1 comma A2 was what? A1 was getting a head or tail. A2 was getting a 1, 2, 3, 4, 5, 6 outcome of throwing a dice, right? So probability of A2 given A1 is equal to head, let's say. So that means A1 head has already occurred. That's certain. That's a data point for you. Given that, what is the probability of A2? And then you can find out different values of A2 and different probabilities. So in the conditional case, whatever is on the conditioning variable, that means you have observed it. That's why you call it probability of A given B has occurred. We don't say has occurred, we said A given B. But the actual statement is what is the probability of event A given B has occurred. So that's the actual statement. For brevity, we don't say has occurred, obviously. Okay, so this is the product law, and this is very useful, like Markovian assumption and all of those assumptions that we will see in this course are based on this thing. Now, this is only two variable. If I generalize it, it will be probability of x1, x2, x3, xn. So I have n variables, right? This will be equal to probability of x1, probability of x2 given x1, probability of x3 given x1 comma x2 dot 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 probability of xn given x1 to n minus 1. x1 to n minus 1 means x1 comma x2 comma x3 until xn minus 1. This is the joint, the product law in action in multivariate setup, right? And I am going to claim that whatever you do in probabilistic machine learning, one way or the another, that is going to be an application of this two law. Whatever you do is the application of only this two law. In different way, in different sequence, you can go from right hand side to left hand side to right hand side, all of those things you can do, but it is going to be application of this sum law and the product law. It's going to be that. Okay. And again, remember that although I'm writing in terms of probability, the same law holds in terms of the PDFs, in terms of the distribution. Distribution also you can write in this exact form. And also take a note that I have written from x1 because that is a choice, that is my choice. You can say that I will start from x5, x10 given x5, do whatever you want and it holds. There is no unique sequence in which you have to go for this law to hold. You can decide where to start, where to end. For example, it can very well be probability of x5, probability of x1 given x5, probability of x2 given x1 comma x5 and go from there. So that sequence does not matter. In general, this decomposition will hold independent of the sequence. But the sequence does matter when you are trying to look at the causality of data. When you are trying to look at the causality of data, so learning causality of data means finding out this unique sequence for this. Because by writing this sequence, I am saying that occurrence of x1 does not depend on anything. x1 is like a parent. Once x1 has occurred, that will influence x2. Once x3 has occurred, that will be influenced by x1 and x2. So when I'm writing in this, I am bringing an inherent causality into the data. Again, causality is not part of this course, but because I am discussing about this, it is important to state that this decomposition is not unique, but given data, if you try to learn a unique decomposition, that is equivalent to learning or finding causality from data. Okay, and in that case, some of these things will come out to be independent, and all of those things will happen, right? Any question on whatever we have discussed till now? Is there any doubt, question, anything you want me to repeat? We have just talked about two things, sum law and product law, nothing else. No? Okay. If there is no question, let us go to the third law, which is application of these two laws, which is the Bayes law, right? The whole area of Bayesian statistics, Bayesian machine learning is based on this one law, which was proposed by Bayes and is known as Bayes law. So probability of A given B, Bayes law helps you find it out, okay, is equal to probability of A, probability of B given A divided by summation probability of A, probability of B given A, sum over A. A or small a I can write A, anyways, that's fine. Okay. This is the Bayes law. This is nothing but 2 or 3 times application of the sum and product law. It's just that. And you can see it. I've written A given B, right? So look at this. A given B or B given A, let's take A given B. A given B is equal to what from this product law? Probability of AB divided by probability of B, right? So probability of A given B is equal to probability of A comma B divided by probability of B, right? Now probability of A comma B, if I write it again in the product law form, what will I get? Probability of A multiplied by B given A. So I can select the opposite sequence anytime. As I said, the sequence is not unique. So probability of A, probability of B given A divided by probability of B. From the sum law, what is probability of B? Sum over probability of A comma B, sum over A. Sum over A, probability of, everyone agrees? That is the sum law. Now inside that A comma B, you again decompose as I have done in that numerator. You get the Bayes law. You get the exact thing. So probability of A, probability of B given A divided by summation over A, probability of A, probability of B given A. So 3-4 times I just applied this sum and product law, that's all. And no matter what calculation you are doing, it will be application of these two laws. Okay. So this is your Bayes law, which is used quite often, and there are some terminologies here in probability of A, for example. Later I will start calling it prior. Probability of A will become prior. Probability of B given A will become likelihood. And what is that? The denominator is what we actually want to learn in generative modeling. So that will become the data. So this comes from, you want to find a probability of theta given data. Theta is the parameter you want to estimate, data is what you are observing. If you write theta given data, you will find probability of theta. multiplied by probability of data given theta divided by probability of data. So if I write it in this form, right? So hmm, depends, right? Where which one came when. I mean, I am putting it in a sequence, not necessarily that everything came in that sequence. Bayes' law came much before. Bayes was a gambler. He came up with the law because he wanted to win in gambling. That is how he was not a mathematician. He was a gambler. He wanted to win, so he came up with that law. So at that time it was law. Other things followed later, and things came later, right? So there is a historical reason for that. Just like the definition of random. Why is it a random variable? I was saying last time, right? Or something like that. Okay. So what I was saying is that probability of theta given d, where d is my data, theta is some parameter I want to estimate. I'll give you one example. I'm tossing a coin. Suppose I have a coin. Okay. I can decide to toss the coin n number of times. Right? So if I toss the coin n number of times, I will observe what? Some sequence of head and tail, some collection of head and tail, head, tail, head, whatever, right? So what is this head, tail, head? That's my data. That's my observation from the experiment I have performed. Right? Now suppose I have that coin, I have a coin. I ask you, is this coin biased or unbiased? You do not know. The coin being unbiased is an assumption we make. And by making that assumption, we make probability of head to be equal to probability of tail. But how do you know a coin is biased or unbiased? You do not know. So how will you, if I give you a coin and ask you that, can you tell me, is the coin biased or unbiased? What will you do? You will perform experiment and try to find out probability of getting head. And you will see that if you can get, or what is the probability of head you are getting, it is closer to 0.5 or not. If it is closer to 0.5, you will conclude that, okay, probability of head is 0.5253 with n number of experiments. So let us conclude that it is unbiased with based on some hypothesis, right? We'll have some null hypothesis and we'll find it out. Right? That's what you will do. But that means you need to find out probability of getting a head given data. The data is you have performed n number of experiments, you have observed head, tail, head, whatever. That's your data. You want to find out theta, so the theta will become your probability of getting head or tail, whatever you want. So you will want to find that out, right? Which means you will want to find out this thing. Correct? So, and now you will use the Bayes law directly or indirectly, but you will probably, if you want to find it out, you have two ways actually. So one of the ways you will go this route. Right? One way is you will go this route. And when you go this route, you can see in the denominator what is appearing. Data. That is intractable. You don't know that thing. And generative models helps you in finding or learning that probability of D only. So that is the new denominator is what you learn in generative model. Okay. I generally don't draw this comparison in this course, but because this time it's on generative model, I'm drawing this comparison. So that is what you learn. And if you learn that, you can now sample from that. What will you get? Either a head or tail with something, right? That's what you will end up getting, right? It is a very simple example because it's a head and tail. In real case, each of this data will be an image of, let's say, 1024 cross 1024 pixels, and or it will be some time series data, each of the data point, and you will need to learn that distribution over those time series. So that is much more, that will become much more difficult. In this case, it's simple, but it will not remain simple when each of your data point is an image. when each of your data point is a time series, let's say music, right? Let's say some signal, you're doing some monitoring kind of problem, right? When I say image, it can be ultrasound, it can be a MRI image, and so on and so forth. And in that case, this finding out this D is what we will be talking about in this course, right? Repeat. Probably D. Correct. Evidence. No, no, no. We don't even go to the posterior distribution. P of D is what you want to find out, and D, that P of D will be parameterized by some phi, let's call it, not theta. So that's what we will do. Now, using that, do you want to go to theta the given D? You might not. If you're solving an inverse problem or somewhere, you will probably want to find out the posterior. Again, for everyone else, because he asked this, I'm using this terminology posterior and all of those things, I'm not defined it yet. But so for some problem, if you need that, you can use this generative model to also solve that. But normally you will not need that. You will only need probability. Okay. Anyways, because the terminology came, let me spend 5 minutes defining this. So this is known as posterior. Posterior probability, posterior distribution, either of this can be. In this case, it's posterior probability. If I write in terms of PDF, it will become posterior distribution, right? P of theta, this term is known as prior. Okay. This term is known as likelihood. And this one is known as evidence. Okay. I'm coming to that. I'm coming to that. That I will discuss next. Okay. So these are the terminologies. P of theta given D is known as the posterior. P of theta is known as the prior. P of D given theta is known as the likelihood. P of D is known as the evidence. Why are these names? And how will you know these things? Let us discuss that, right? By name itself, P of theta is known as prior. It, by definition, means what is your belief about theta, which is unknown by the way, before you have observed any data. Prior means your belief about theta in this case, even before you have observed any data. I'll give you two examples, right? First example, let's say in a given problem, my theta is my some length I want to infer. Okay, some length or some elastic modulus, something like that. So let's take elastic modulus. So let's say I have this pen. Okay, elastic modulus is a material property. I can deform it and measure it. Okay. Now this pen is manufactured by XP Pen. XP Pen is manufacturing thousands of such pens. I take 10 of those samples or 20 of the samples. For each of the samples, I can measure E, and that will become my data, right? But actually, E you cannot measure. You will measure displacement. E is actually an inferred quantity. You will measure displacement, right? But even before I have collected any data, even before I have any of this pen, I know that my objective is to infer a material property elastic modulus which is non-zero. Elastic modulus will not be zero, I know that. So that's my belief about this property known as elastic modulus, even before I have observed any data. So that means my prior distribution should be something that is non-negative, like a log normal distribution, which will come later. So P of theta prior is your believe about theta before you have observed any data. Okay, what is prior? And that's why you call it prior. Prior to observing the data, what is your belief? Right? Then here is P of D, P of theta given D. Theta given D means you have observed the data. Now what is your belief? So that's why it's a posterior. After, posterior means after. So after you have observed the data, now has your belief changed? So for example, before I have measured any of these measurements, right? My belief was it is greater than equal to 0, or at least greater than 0 even, right? So that means what was the range I was working with? 0 to infinite. So my prior belief was 0 to infinite. After I observed and do some measurements, let's assume this to be steel, for example, for a second. So then I know it will come out to be somehow, let's say I observe data, some is 190, some is 210, some is 205 and all of those things. My posterior should not, my belief should not be 0 to infinite. It should be somewhere between, okay, if I'm observing 190, 195, my belief should be somewhere between 180 to 220 maybe. And then it should have some mean and standard deviation and all of those things. So theta given D is my belief about theta after I have observed the data. And that's why we call it posterior. Clear? Then there is P of D. We call it evidence. What does evidence mean? Evidence means whatever data you have observed. That's what evidence, right? In crime or whatever, the police says that we have this evidence. Evidence means this is the data we have got. That's why P of D is what? D is data. It is probability of those data. That's why you call it evidence. Lastly, there comes the term likelihood, right? Likelihood is probability of D given theta. That's what we call it likelihood. Because this is telling you for some theta, you don't know theta by the way, but for some theta, how likely is it that you will observe what you have observed? I'll give you an example, and this is an example I give every time actually, a common example. I created it some time back. So suppose I am traveling from Delhi to, let's say, Kanpur. IIT Kanpur, I have a friend who has called me, I'm traveling to Kanpur from Delhi, right? It's what, 500 odd kilometers from here. Now, how can I travel? I can take bus go to Kanpur, right? I can have my own car, I can drive it. I can take a train. I can even take a flight. There are flights going to Kanpur, right? So there are these 4 modes of transportation that I can use for traveling from Delhi, IIT Delhi to IIT Kanpur, right? These are the 4 modes that I have, let's say. Now, my friend is there in Kanpur. I told him that, okay, I'm leaving now from Delhi. And let's say that was 10 a.m. some fine day, right? And then I reached his place around, I don't know, maybe 3:30 p.m. Okay, in between I never contacted him. I never talked with him. He just know that I left IIT Delhi at 10 and he knows that I reached Kanpur at 3:30. So that means it took what, 5.5 hours kind of time, right? So what will my friend infer? How did I travel? Did I take a bus? Did I take a car? Did I take a train? Did I take a flight? What will he infer? See, bus 500 kilometers I cannot reach in 5.5 hours. Same for car. Bus will probably take 10, 12 hours. Car will take 8 hours. Train, if I take a Vande Bharat or something like that, I can probably reach, given that there is no delay or something like that. Flight also I can reach, but then there is a 2 hour before prior I have to go to the airport, and all of those things will go in my friend's mind. And he will probably infer that most probably, he is not sure, most probably, I have traveled using some high speed train, right? So in this example, what was the data for my friend had? 5.5 hours travel time. What was the theta parameters that he was mode of transportation, these 4 modes of transportation. Now in his mind, what was he doing? He was saying, what is, if I go by, what is the probability that it will take me 5.5 hours to travel, given I travel by a car? And in his mind, without him knowing, unknowingly, it might have given a probability of 0.1. Yeah, if he drives at some 100 odd kilometers on an average, he will reach in 5 hours. That is not possible, but that's why, because that is not feasible, so 0.1. Similarly, in his mind, again, unknowingly, he has calculated that probability of it will take 5.5 hours, given I go by train. Okay, Vande Bharat is possible, so probably the probability is 0.6. And similarly for bus, it is 0.05 maybe, and like that for the others. And obviously this sum should go to 1, right? From there, he inferred that the most likely way I have traveled is by train, right? That means train is most likely, or train is the most likely mode of transportation that explains the travel time being 5.5 hours. So I am using the term likely again and again. That's why we call it likelihood, right? That's why we call it likelihood. How likely is a given theta to explain the data? So that's why we call it likelihood. And the problem that was being solved in his brain without him knowing is known as the maximum likelihood estimation. He was looking at these 4 possibilities, finding out which is the mode of transportation that maximizes the likelihood, that maximizes probability of d given theta, right? So that's why we call it the maximum likelihood estimation, and we'll need it later in the course, like MLE or maximum likelihood estimation. But maximum likelihood estimation means you find out the likelihood, maximize it, and whatever maximizes it is your answer. In most cases, when you do it, you will get your common sense answer. Okay, you get the common sense answer. So that's why this is known as likelihood, and the method is known as the maximum likelihood estimation. If you use that one, maximum likelihood estimation is not a Bayesian approach. In a Bayesian approach, you don't only rely on likelihood, but also on prior. When you combine or use both prior and likelihood, you get a Bayesian approach, or somewhere in between a map also. Okay, which is known as maximum a posteriori estimate. Okay, so left hand side, that is known as posterior, that tells you about your belief about something after you have observed the data, theta given d. P of theta is your prior, that is your belief about that parameter before you have observed any data. P of d given theta is your likelihood, that tells you how likely a theta is to explain the data you have observed. And P of d is the evidence, data, evidence directly connected. So these are the 4 terminologies that you will have to deal with: posterior, prior, likelihood, evidence. And posterior is proportional to prior times likelihood, or posterior is equal to prior times likelihood divided by evidence. Okay, any question on this part? So these terminologies are clear, more or less. Okay, so this is what you will be using throughout this course. But what we were talking about was Bayes law, right? What we were talking about is here. So we are talking about Bayes law. Moving ahead. Moving ahead. there is something known as statistical independence. So, any intuition when you will call two events A and B to be independent? Not the equation, but definition, let's say. Suppose I have two events, A and B, random events, obviously. When will I call A and B to be statistically independent or independent? When occurrence of one does not influence or change my belief about the occurrence of other, right? Mathematically, that is equal to probability of A given B is equal to probability of A, right? That's the actual from the whatever definition you said. That's what is coming from there. But when we talk about independence, we go to the intersection one. That's something that is derived from this actual definition, right? So from this definition, that occurrence of one event does not change your belief about the other event, right? So that means A given B will be equal to probability of A. And similarly, probability of B given A will be probability of B. When this condition holds, that means whether A has occurred or not, or whether B has occurred or not, is inconsequential to the probability of A. Whether B has occurred or not is inconsequential to the chances of observing A. Right? For example, whether I am eating veg or non-veg today should not control whether tomorrow there will be rain or not. It does not matter, right? Whether tomorrow is rain or not is depends on 10 other factors. What I'm eating is not one of those factors. Right? That's statistically independent. So that means outcome of one event should not influence the outcome of the other. Now from here you can very easily show that the well-known thing that we always use is probability of A comma B is equal to probability of A into probability of B. And this comes again directly from the product law times the definition, you get it. A, B given is equal to B, you end up with this. Again, application of product law, right? Along with obviously the definition. Now, how many of you are from School of AI? 1, 2, 3, not much, right? Okay. So this is a common question in School of AI interview, right? That if two events are uncorrelated, right? So two events are uncorrelated, right? Or not uncorrelated, two events are disjoint, let's say, right? Two disjoint events, mutually exclusive. So then, what can you say about them being independent or dependent? Who said nothing? Why nothing? Mutually exclusive means what? Let's go by the definition. If one occurs, the other does not occur. Is your belief changing about that? If one occurs, you know the others is not occurring. It's a highly dependent event, right? But people get confused between disjoint and independence. Disjoint means both of them cannot occur together. That does not mean they are independent. Independent means occurrence of other one should not influence your belief about the other. So if you are disjoint, if I know one has occurred, then the other has or will definitely not occur. If now it is day, then definitely it's not night. Right? So I'm now certain about it. It's a probability of 0 if one has occurred. It's highly dependent actually. But this is a very common confusion people have because when they're not occurring together, you think like, okay, they are independent. But actually when they're not occurring together, they are highly dependent. Because if one is occurring, other is not occurring. You know that for sure. Okay. Again, I said this is a very common question in School of AI interview. I'm not sure if it was asked to one of you, but it's a very common question there. Okay, along with many other questions, but this is one of the common ones. And often students do confuse and answer wrongly for this, right? So whenever you have a question like this, think. I mean, it's not that difficult, but just give yourself a moment and think, right? Statistical independence, okay? There is also a condition of or something known as conditional independence. So it is possible that A and B are not independent, but given a third event has occurred, they become independent. So there is this concept known as conditional independence. Conditional independence. Probability of let's say A comma B given C is equal to probability of, I mean, I'm using the last one, I can also use the first two, but that's okay. A given C multiplied by probability of B given C. But probability of A comma B is not equal to A, probability of A multiplied by probability of B. Right? And this has huge application in causality. I was talking about causality a little while ago. So this has huge application in causality, and I'll give you one example of that. So there is actual data, and in that actual data it has been observed that, okay, the two data are about what? So there are two data sets, right? And these are time series data. The first data is about seasonal or year wise, month wise data on ice cream sale. The first data is on ice cream sale. The second data is on shark attack. Okay, shark attack on human. Shark attack on human. The first data is on ice cream sale. Now it is observed that these two data, the pattern matches exactly. Whenever ice cream sale increases, shark attack increases. Whenever ice cream sale reduces, shark attack reduces. Okay. So apparently, if you find out these two data and somehow calculate the probability, you will find them to be dependent. Although they are actually correlated, not dependent. But if you find this probability, you will find them to be dependent. Okay. Exactly. So that is the event C, which is season. So there is an event C that influences this A and B, which is season. And as correctly pointed out, in summer, people ice cream sale increases. People eat more ice cream, right? And in summer, people go to beach more. When you go to beach, the shark attack increases. If you do not go to beaches, I mean, how will there be a shark attack? So it is this event C in that case is season, which influences both A and B. If you remove C from the picture, A and B seems dependent, actually correlated, to be very honest. But as soon as you bring the C into factor, this A and B are conditionally, I mean, this thing comes into picture. Right? And this is a classical example that we give to explain correlation versus causality. Why causality is important and why correlation is not the answer. There is this whole idea, right? This ChatGPT and large language models, they are based on correlation, right? And that's why they cannot achieve AGI, generalized intelligence, right? And people, there is a whole line of argument that we need causality. We need to understand the causality to actually be able to achieve human-like intelligence or whatever, right? A generalized intelligence. So this whole debate of AGI, this is a central part in that, right? You need to learn this kind of decomposition to actually do that. Okay. So this one, if I have to draw, so there is a nice representation actually. So to the shark attack one, right? C is the season, and C influences A and C influences B. Right? You see, I'm showing an arrow. This is known as directed graph. To be very honest, this is directed acyclic graph or DAG. So there is no cycle. And using this directed graph or learning this directed graph is the goal of learning causality. You want to learn these things. Given data of ABC, you want to learn this. That's what learning causality means. In general, if you don't have this arrows, you can write probability of A, comma B, comma C as 3 different ways maybe or maybe more. A, B given A, C given B, comma A, C given A, B, comma A given A, comma C, and all of those. But as soon as you have this arrow, you know there is only one decomposition. Probability of A multiplied by probability of B given A multiplied by probability of C given A. This is your decomposition for A, comma B, comma C. It becomes unique. That means you have learned the exact causal relation. And all of this is stems from or exact DAG, directed acyclic graph. And all of these are related to this concept, right, of learning the reason or causative pattern, learning this directed acyclic graph. Okay. Any question? Yeah, that doesn't matter. I mean, correlation can be anything, but correlation does not necessarily mean causality. Correlation and causality are two separate concepts.
If there is no correlation between A and B, that time also we can have this conditional.
Unlikely. If there is no correlation, then there, I mean, you know, right? Things can be dependent and still uncorrelated, but if things are uncorrelated, they are, I mean, if things can be uncorrelated and still dependent, but if things or events are independent, they are uncorrelated. For example, event A and B, they can be uncorrelated and still A and B can be dependent. But if A and B are independent, then they will definitely be uncorrelated. So independence means absence of correlation, but absence of correlation does not mean independence. Because whatever correlation you calculate are generally linear correlation. You calculate those correlation, those are correlation coefficients, whatever you calculate, those are linear. So if you take one easy example is take y equal to x square and let x be -2, -1, 0, 1, 2. I'm telling you the 5 values. Now calculate correlation, you will get 0. But you know y equal to x square, they are dependent. Because it's a parabola equation, right? Y equal to x square. So that's why you get it. It's not linear, so you don't get it. Okay. Okay. So this was statistical independence. How much time I have? 20 minutes, 15 minutes. Okay. This was statistical independence. Now, I think this was all about probability I wanted to talk. Now let us go to the distribution part. We talked about random variable last time, but I told I'm using this term distribution again and again, but I have not yet really defined what is distribution. So let us try to define it. Before I forget, attendance. Okay. Okay. So now, random variable. Can you remind me what is a random variable? We defined it last time. It's a function that maps from the event space to the real space. Real space can be multivariate or matrix even, but it's a function. It's not a variable that maps deterministically, not randomly, from the event space to some real space. Example, head and tail is your event space, head equal to 1, tail equal to 0 is your random variable or real space. And whatever maps it is your random variable. We discussed this, right? Random variable is a function that maps from the event space to the real space. Now, this random variable, how many types of random variable can be there? 2. This variable can either be discrete or continuous, right? So random variable, first let me write. It's a function, let me write that, x that maps from event space to, let's say, some real space, right? So that's what random variable is. Type of random variable, discrete, or continuous, right? Discrete means it will take discrete values, head and tail, 1 and 0, discrete. Continuous means it will take continuous value, height of students in this class. If that's a random variable, if I start measuring, it will become continuous value, right, in decimals. And if a new student is coming, he or she can have a height which does not exist in this room, can have a different height. Head and tail, it will be between those two, right? Now, for discrete variable, there is something known as probability mass function. And for continuous random variable, there is something known as the probability density function. What is the probability mass function? First of all, it's a function. The name itself has function. It's a function that has certain properties. Okay. What are the properties? Just two properties. The first property is that the value of that, the function itself, will be between 0 and 1, touching 0 and 1. So 0 less than equal to that function less than equal to 1. That's the first property. Okay. What is the second property? When you sum over all the possible values of x, it will give you 1 unity. That's the probability mass function. So this you define using probability mass function. The continuous you define using probability density function. So if I go to probability mass function, fx x, this is how you denote it. Fx x means it's a mass or density function that will not change of variable capital X, which is at the subscript, and small x inside the bracket is the value it is taking. So capital X is the random variable, small x is the value that random variable is taking, or as we call it, later we will call it realization of the random variable. So fxx is a PMF if 0 less than equal to fxx less than equal to 1, right? If this is the range, then it's the first property. It is between 0 and 1. And second one is sum over all values it can take. This is equal to 1. Okay. If these two properties are satisfied, any function that satisfies these two properties is a PMF. Okay, any function. The other one is PDF. Let me use the right hand portion of the slide. If I go to PDF, fxx, again it's a function, any function that satisfies this two property is a PDF if, and I can write IFF, if and only if, that's also fine. Now what are the two properties for PDF? Greater than equal to 0. It can be greater than 1 also. PMF is always between 0 and 1, touching 0 and 1. PDF can be greater than 1 because it's not probability, it's density of probability actually. So it can be greater than 1, keep that in mind. PDF is not bounded on the upper hand side. Okay. I mean, there is one special PDF where this value can be infinite, direct delta function. Okay. When something is very certain, so then at that point it's infinite. So fxx greater than equal to 0, So it can be greater than 1, keep that in mind. And the second thing is integration over okay. So these are the definition of PMF and PDF. Very similar, slight difference, but that slight difference you take a note of, which is specifically the one part. Okay. And I'll repeat, PMF is probability, but PDF is not. If you have to find the probability, you need to integrate the PDF between certain range, and that gives you a probability in that range. Okay. So PDF is not probability, or rather the way I like to think it about it, if you are from mechanics, you will relate. Mass is probability, density is not. If you have density, to find out the mass, you have to multiply it with volume or area. So when you integrate it out, you kind of find out the volume or area, right? So that's how you can relate that mass versus density thing. Okay, that helps you remember this. Okay, if you have PMF and PDF, you can use it to find out your some of the important statistical quantities like expectation, which is also mean, variance, standard deviation, same kind of thing. Not same, but similar. Then kurtosis, skewness, all these quantities you can find out. I like to call them moments. So the first moment is mean, second moment is variance, third moment is skewness, fourth moment is kurtosis. So keep this term moment in your mind, that will help. Okay. So you can find those out. How? So your mean is expectation of the variable x with respect to the PDF f, let's say, right? So capital X is having a PDF f. So this expectation is with respect to this f. I mean, in books you might not find this f always, but sometimes it's needed. Integration of x f x x dx. I have not written the limit, but the limit is minus infinite to plus infinite. Okay, so all possible range. So this is your mean or the first moment. Let's go by moment, and that's easy. So it is called first moment because the power of x is 1. If I make the power of x to be 2, I will start calling it second moment. Again, variance also relies on power of 2, so we also call variance as second moment, but you can also say e of x square as second moment, that's fine. I mean, very slight difference, but yeah. So in this, you can change the power of x, and whatever is the power of x, that is the order of moment you are dealing with. X to the power 5 will be fifth moment, x to the power 10 will be the 10th moment. So x to the p will be the pth moment. So keep in mind like that, right? So this is also the first moment. Right. Similarly, if I have to find out the second moment, that will be integration x square f x x dx, and this is known as e of x square, right? If I have to find out the pth moment, this is the pth moment. Okay, and you can find anything. Now this variance or standard deviation is function of the second moment and the first moment. You can use the second moment and first moment to find out this variance and standard deviation. I'm not going to write it, you read it, and it's one line, you probably know it already. Okay. So these are the statistical quantities you can calculate using your PDF, given that you know your PDF. Yeah. I wanted to also cover distribution today, but I think I don't have time. But let me at least start, right? Some standard distribution. So this fxx, how does it look? What are some of the standard distribution? Again, I'll repeat, this course is about learning this fxx. Learning this fxx from data, that's this course is about. Implicitly, explicitly, that's a different story, but generative modeling is about learning fxx. So we will be doing that. But in the process of learning fxx, it is absolutely essential that you know about at least one or two basic distributions, which is uniform and Gaussian mostly. But we'll cover 2, 3 maybe. But it is important that you know about the basic distributions. Those basic distributions directly will not help you. But without those basic distributions, there exists no generative model. The fact that there exists a basic distribution from which you can sample is the backbone of generative model. I'll repeat, the fact that there exists a basic distribution from which you can sample is the backbone of generative model, or at least one of the backbone. There is one more backbone that you can transform from any distribution to any other distribution. There is a transformation law. So these two combiningly is what generative model is mostly all about. Okay. The first thing is that some of the easy distributions you can easily sample from. You can do things analytically and all of those things. The second thing is that you have a one-on-one mapping between two distributions. There is this whole field known as optimal transport. But in general, even if I don't go to optimal transport, there is this transformation of distribution. And because that exists, you can do this one-on-one mapping. Okay. So it is essential that we talk about at least 2, if not 3 distributions, which is, let's say, Bernoulli, generally not used, but anyways, in generative model, uniform and Gaussian. Gaussian is unavoidable, obviously, but at least this 2, it's important that we talk about, right? So let's talk about Bernoulli for today at least, and then I will stop. Next lecture will start with Gaussian and I will wrap it up, right? So Bernoulli distribution, right? So Bernoulli distribution is generally used, or is used, not generally, forget generally. Bernoulli distribution is used when the outcome of your random experiment is either success or failure. For any random experiment for which the outcome can be categorized as either success or failure, Bernoulli distribution is your thing. Okay. Bernoulli distribution is your thing. What is the PDF or PMF? PMF actually. Of Bernoulli distribution, it is f xx is equal to p to the power x 1 minus p to the power 1 minus x, where x is a Bernoulli random variable and taking two values 0 and 1. 0 means failure, 1 means success. For example, if I toss a coin, if head is success, so x equal to 1. If tail is failure, then x equal to 0 is tail, right? And p is the probability of getting a head, right? And 1 minus p is probability of getting a tail. So it is basically saying that if you get a head, this should give you half not p. And if you get a tail, it will give you 1 minus p. If it is unbiased, both will give you half. So this is the PMF of Bernoulli distribution. Okay. Now if I give you a distribution, if you give you a function, right? Let's say this one. Okay, here this is not complete. Actually, you have to write that x is either equal to 1 or 0, right? You have to write that. Otherwise, I mean, x does not take any continuous value. You should not put x equal to 0.5, for example. It is either 1 or 0. That these are the two values x can take. It cannot take any other value. It can either be head or tail. It cannot be somewhere in between. As simple as that. So now, what I was saying is that if I give you a function like this and ask you, is this a PMF? How will you prove it? First check whether it is between 0 and 1 or not. That is the first criteria. You have to prove that it is always greater than equal to 0 and it is always less than equal to 1. First you need to prove these two things. And then you need to prove that if you do a summation over this, you should get 1. Now if something is in the power, when something is in the power, you cannot get negative. When you do the summation product of two things, it is always greater than equal to 0 is very obvious. Now x is 1 or 0, p is between 0 and 1. So this thing is always less than 1. That is obvious. It will only be equal to 1 when p equal to either 1 or 0. Every time else it will be. So you can very easily prove that it is greater than equal to 0 because of the power, less than equal to 1 because p is between 0 to 1, right? And what the other condition is the sum should be equal to 1. So let us do the sum. So first it will be p to the power 1, 1 minus p to the power 0. That will give you p plus p to the power 0 multiplied by 1 minus p to the power 1. That will give you 1 minus p. The sum will be p plus 1 minus p. P and minus p will cancel out, you will be ending up with 1. So you can easily prove that it's a PMF, it's a valid PMF. Okay, I'm not doing this, but you can do it. Okay, anyway, the derivations are there. I mean, whatever I said just now is there at the end of the slides. There are some 70 odd type slides at the end actually. Okay, maybe more. Obviously, not everything I am covering today, so I'll remove those. Those will go into the next slide, next lecture's type slides. But there is 70 odd type slides at the end of today's lecture, which is for your reading. And many of those things are for I am teaching actually, but there are things which I am not teaching, which are also there. So please read those. Yeah, I'll start uploading this. I have not yet uploaded. So I'll start uploading these slides and the recording also. Okay. So you can prove that it's a PMF, very simple. And you can also find the expectation. What is the expectation of this? How do you find P, right? How do you find out the expectation? Summation of x fx. So it will be 1 x equal to 1, right? Times P plus 0 times 1 minus P. So 0 times 1 minus P will be equal to 0. 1 times P will give you P. So your probability is equal to your expectation in case of Bernoulli distribution. It's a unique property of Bernoulli distribution where your probability is your expectation. It will generally not happen. So mu is equal to P. Variance, if you calculate, that will come out to be what? P into 1 minus P. Variance will come out to be P times 1 minus P. You can calculate it. Okay. And then you can calculate the other properties also. So this is one sample distribution, right? And this is the P I was talking about that you might want to find using Bayesian and maximum likelihood estimation, right? Again, I'll not go there, but you can think about that you want to find out this P, given you have some experiments, some data. Okay, so I'll show you the slides that is there at the end and then I'll stop. So I think I have 30, so let me go to 31. Yeah. So discrete random variable, we are talking about it. Example, joint probability, we talked about it. Sum and product law rule. Conditional probability, Bayes rule. This is a very nice example to study it. It's very interesting. This is known as Bayes rate fallacy. You should study this. Okay. Independence, conditional probability we're talking about. Conditional independence, this is a diagram I was drawing, right? Pairwise and mutual independence I did not cover, but you can check it out. Importance of independence, not so much needed for this course, so I'm skipping it, but basically number of parameters reduces. Random variable, last class, CDF, integration of PDF from minus infinite to x. Mean and variance, expectation, uniform random variable, we'll do it next time. So we covered until this point. From here, we'll do next time. I guess there should be something on Bernoulli also, I'm guessing. Yeah, binary, it's there, right? Mu to the power x. So this slide again we covered. So up to 47 and this one. So this will be there when I upload it. The remaining ones I will actually remove, and I will put them in the next lectures at the end. Okay. So I'll stop here, but before that, is there any question? Remember that I'm covering too many things because it's a review part right now. So you might, I mean, again, most of you are probably aware of prob and stat. So for you, it's like repetition, so boring, and that's fine. It's okay to be bored for 1 or 2 lectures. But if you're not that familiar with prob and stat, you might need to do a course online on prob and stat, because what I'm covering is generally things that are covered over multiple lectures in a prob and stat course. I'm doing things verbally without writing even, right? So those things might be obvious to those who have done a prob and stat course, but for those who have not done or don't remember, please do these derivations. It's 2-line derivation, but do it. Else you will not follow. Okay. But it's a review part right now. We are in the review part, so I'm going a little bit faster. I'll slow down when I go to the actual generative modeling part, which will be new for everyone. Okay. So with that, I'll stop. Thank you. We are meeting on Thursday, by the way. I'll send an email for the practical, and then on Friday for the next lecture. And next week, instead of 2 lectures, there will be 1 lecture, which is on Tuesday, because Friday I'm not here. Okay, that I will take some extra lecture later. So 23rd, there is nothing. Thank you.